Welcome to Methods in Biostatistics. Today, we are going to explore one of the most fundamental ideas in all of science, the difference between parameters and statistics. By the end of this video, you will understand exactly how researchers make massive, world-changing discoveries without having to measure every single individual in the world. Let us dive right in. Let us start with a simple, everyday analogy to build our intuition. Imagine you are cooking a massive pot of soup for a large family gathering. To know if the soup has enough salt, you do not need to drink the entire pot. Instead, you take a small spoon, stir the soup well, and taste just that one spoonful. If that spoonful is perfectly salty, you confidently assume the whole pot is too. In biostatistics, the entire pot is the population, and the spoonful is our sample. Building on our soup analogy, let us define these terms formally for scientific research. A population is the complete set of all individuals, items, or data points that we genuinely want to study. It is the entire group of interest. A sample, on the other hand, is a smaller, randomly selected subset of that exact same population. We use the small, manageable sample to make smart, educated guesses about the giant, unmanageable population. This relationship is the core of all statistical analysis. Now that we know what a population is, we can define a parameter. A parameter is a numerical value that describes a specific characteristic of the entire population. Because it represents the whole group, a parameter is a fixed, true value. However, it is almost always completely unknown to us in the real world. In mathematical formulas, we represent parameters using Greek letters, like mu for the mean, or sigma for the standard deviation. These letters signal that we are talking about the absolute truth. In contrast to a parameter, a statistic is a numerical value calculated only from our collected sample data. Because we can actually measure our sample in the real world, statistics are known values. However, they are variable. They change depending on which specific sample you happen to pick on any given day. We represent statistics using standard Roman letters, like X bar for the sample mean, or S for the sample standard deviation. These letters remind us that we are looking at an estimate. You might be wondering, why do we separate these two concepts so strictly? In the real world, especially in biology and medicine, it is physically impossible, far too expensive, or simply too time-consuming to measure every single individual. For example, if we want to know the average blood sugar level of all diabetic patients in a country, we cannot possibly test millions of people. Instead, we test a sample, calculate a statistic, and use it as our best estimate for the unknown population parameter. Let us look at how this works mathematically, starting with the population mean. Conceptually, finding an average is simple. Add everything up and divide by the count. Here, the Greek letter mu represents our unknown population parameter. The formula requires us to use the capital sigma to add up every individual measurement, represented by capital X sub I. Finally, we divide by capital N, which is the absolute total number of individuals in the entire group. As the population size increases, this becomes much harder to calculate. Because the population mean is usually impossible to find, we rely on the sample mean formula instead. Conceptually, this comes from the exact same idea of averaging, but applied only to our subset. We use X bar for the sample statistic. We sum up the lowercase x sub I values, which are just the measurements from our sample. Then we divide by lowercase n, the sample size. Notice the deliberate shift to lowercase letters. If our sample size n increases, our statistic x bar will generally get closer and closer to the true population parameter mu. Now that we have our formula, let us apply it to a concrete example. Imagine a pond with exactly 50 frogs. Catching all 50 to find the true parameter mu is too difficult. Instead, we catch a sample of 5 frogs and weigh them. We substitute these 5 weights into the numerator of our sample mean formula and divide by our sample size of 5. Adding the weights gives us a total of 110 grams. Dividing by 5 gives us a sample statistic of 22 grams. This 22 grams is our best educated guess for the true average weight of all the frogs in the pond. Let us look at a more realistic clinical application. A pharmaceutical company tests a new heart rate drug on a sample of 100 patients. The problem tells us the total sum of all heart rate decreases is 1,200 beats per minute. We chose this formula because we need the average effect. We do not need to add up individual numbers here. We just plug the total sum directly into our numerator. We divide by the sample size of 100. The result is 12 beats per minute. The company will report this statistic to medical regulators, estimating that the drug will lower heart rates by about 12 beats per minute for the general population. To visualize everything we have learned, take a look at this diagram. On the left, we have the large population circle, which holds the true hidden parameters like mu and sigma. Because we cannot measure it directly, we follow the top arrow and take a random sample. This gives us the smaller circle on the right. From this sample, we calculate known statistics like x bar and s. Finally, we follow the bottom arrow, using statistical inference to estimate the unknown parameters of the population. This continuous cycle is the foundational bedrock of all biostatistics. We have covered a lot of ground today, so let us review the key takeaways. Remember that a parameter is a fixed, usually unknown truth about an entire population. A statistic is a known, variable fact that we calculate from a smaller sample. Because we cannot measure every single individual in the real world, we rely on these statistics to act as our window into the true nature of the population. You now have the foundational knowledge to understand how medical studies make estimates about the real world. Great job!